Integration by completing the square. Okay, so let's begin with the topic of integration by completing the square. As you know, in the previous sections, we've been practicing integration techniques for fairly straightforward quadratic expressions in the denominator. Specifically, we looked at integrals where the denominator was something like x squared minus a constant minus x squared, or simply x squared plus a constant. We had nice, neat formulas to handle those directly. However, real-world problems aren't always so cooperative, are they? Often, you'll encounter integrals where the denominator isn't one of those simple forms. Instead, it's a more general quadratic polynomial, represented as a x squared plus bx plus c. Now, the integration formulas we learned earlier won't work directly on this general form. We need to manipulate the expression first. What we need to do is transform this general quadratic, a x squared plus bx plus c, into one of those standard forms we do have formulas for, like x squared minus a constant, and so on. The technique we use to do this transformation is called completing the square. It's an algebraic method that allows us to rewrite the quadratic expression in a more convenient form for integration. We'll be diving into the details of how to complete the square in the following slides. But for now, just understand that it's a crucial step to make these more complex integrals solvable using the techniques we already know. The concept of completing the square. This slide formally defines what completing the square is. Completing the square is an algebraic technique, meaning it's a set of steps we follow used to rewrite a quadratic polynomial, which is an expression of the form a x squared plus bx plus c. Remember, b and c are just coefficients or constants in front of our x terms. The goal of completing the square is to transform this general quadratic expression into a very specific form. And this is crucial for making those integrals solvable using the formulas we already know. We want to rewrite it as a multiplied by a squared binomial, that's something in the form of x plus h, all squared, plus or minus a constant, which we'll call k squared. So essentially, we're aiming to get our quadratic into a form that looks like a times the quantity x plus h squared plus or minus k squared. This form is much easier to integrate, as we'll see in the following slides. Think of it as rearranging the furniture in a room. It's still the same room, but it's organized in a way that makes it easier to navigate. We'll be looking at how to do this rearrangement in the next slide, step by step. Okay, so let's move on to slide 2. As we discussed on the previous slide, we often encounter integrals with quadratic expressions in the denominator, but directly applying our standard integration formulas isn't always possible. That's where completing the square comes in. Step-by-step algebraic process. Step 1, factor out the coefficient of x squared. Now, this is important. If the number in front of our x squared term, isn't equal to 1, we must factor it out. This means rewriting the expression as a multiplied by the entire quadratic inside brackets. So, we have a x squared plus bx plus c, becoming a multiplied by x squared plus b over a x plus c over a. This is just a bit of algebraic manipulation to set us up for the next step. Step 2, focus on the linear term. Next, we need to concentrate on the term with just x in it. Inside our brackets, that's b over a x. We're going to take that coefficient, b over a, and divide it by 2. This gives us b over 2a. This value is crucial because it's going to help us create that perfect square trinomial. Step 3, add and subtract the square. This is the heart of the completing the square technique. We're going to add and subtract the square of b over 2a. That is, we add and subtract b over 2a all squared. This looks like b over 2a to the power of 2. We do this inside the brackets. Let's write that out. A multiplied by x squared plus 2 times x times b over 2a plus b over 2a squared minus b over 2a squared plus c over a. Now, it might seem like we're just adding and immediately subtracting the same thing, and you're right, we are. But this is deliberate, because it allows us to create a perfect square trinomial without changing the overall value of the expression. Step 4, simplify to the standard form. If you look closely, the first 3 terms inside the brackets, x squared plus 2 times x times b over 2a plus b over 2a squared, these form a perfect square trinomial. They can be factored into x plus b over 2a all squared. So we can rewrite the expression as a multiplied by x plus b over 2a squared plus c over a minus b over 2a squared. And that's it. We've successfully completed the square. Okay, so let's move on to the actual how-to of completing the square. This slide details the step-by-step algebraic process. Remember from the previous slides, we're aiming to transform a general quadratic expression, something like a x squared plus bx plus c, into a form that's easier to integrate, specifically, something involving a squared binomial. Now, this might seem like a lot of steps, but with practice, it becomes quite mechanical. And remember, we're doing this so we can then apply standard integration formulas, as we'll see in the following slides. The goal is to get our quadratic expression into this form so we can easily integrate it. Application to integration. Okay, so we've spent the last few slides learning how to rewrite quadratic expressions by completing the square. Now, let's talk about why we do that, specifically, how it helps us with integration. This slide outlines the two main types of integrals where completing the square is particularly useful. First, we have integrals of rational functions. Now, a rational function is simply a fraction where both the numerator and denominator are polynomials. In this case, we're looking at integrals of the form integral of dx, which represents a tiny change in x, divided by a quadratic expression, x squared plus bx plus c. Remember, b and c are just constants. Completing the square on that quadratic in the denominator allows us to transform it into a form we can integrate using standard formulas, as we discussed earlier. Secondly, we have integrals of irrational functions. These are integrals where we have a square root containing a quadratic expression. Specifically, we're dealing with integrals of the form integral of dx divided by the square root of x squared plus bx plus c. Again, completing the square inside the square root simplifies the expression, allowing us to use standard integration formulas. You'll see in the examples coming up, and this is important, that the core idea is always the same. We complete the square to get the denominator, or the expression under the radical, into a more manageable form. Then, we can apply a simple substitution, and finally, use one of the standard integral formulas we've already learned. So, keep these two integral types in mind as we move forward, because they represent the primary applications of the completing the square technique in integration. General procedure for integration. Okay, so let's move on to outlining the general procedure for tackling these integrals, where we need to complete the square. This slide, slide 5, summarizes the steps we'll follow. Remember, we've already discussed why we complete the square, to transform those tricky quadratic denominators into forms we can easily integrate using standard formulas. Step 1, the very first thing we do is, as the slide says, complete the square for the quadratic expression sitting in the denominator of our integral. We went through the entire process of how to do that on the previous slides, so make sure you're comfortable with factoring out the coefficient of the x squared term, finding the value to add and subtract, and ultimately rewriting the quadratic in that perfect square plus or minus a constant form. This is the foundational step. Everything else builds on it. Step 2. Once we've completed the square, the next step is a simple but crucial substitution. We let u equal x plus b over 2a. Now, pay attention here. B is the coefficient of the x term in our original quadratic, and a is the coefficient of the x squared term. So, we're defining u in terms of x. Because we've defined u in terms of x, it's really important to remember that this also means that the differential du is equal to dx. This substitution simplifies the integral, making it easier to recognize which standard formula to apply. Step 3. Now that we've made the substitution, we need to identify which of the standard integration formulas, we discussed 6 of these earlier, applies to the resulting integral. This is where recognizing the form of the integral after the substitution is key. Is it in the form to use an inverse tangent, a natural logarithm, or something else? Careful consideration is needed here. Step 4. Finally, once we've identified the correct formula, we integrate. We apply that standard formula to find the integral in terms of u, and then, very importantly, we substitute back the original expression for u in terms of x. This gives us the final answer in terms of our original variable, x. So, to recap, complete the square, make a linear substitution, identify the correct standard formula, integrate, and substitute back. If you follow these 4 steps systematically, you'll be able to solve a wide range of integrals involving quadratic denominators. We'll see this in action with some worked examples on the next slides, so don't worry if it doesn't all click immediately. Worked examples. This slide addresses that. It points out that while these integrals might seem a bit abstract at first, they actually pop up quite frequently in real-world applications, particularly in fields like physics and engineering. Specifically, the slide mentions 2 examples. First, calculating the electric potential of a point charge. Now, you'll learn the details of that in your physics classes, but essentially, determining the electric potential often requires integrating a function where the denominator is a quadratic, and completing the square is a key step in setting up that integral. The second example is analyzing the motion of a damped spring mass system. Again, you'll get the physics behind this later, but the mathematical model describing the motion often involves integrals of this same type. So, understanding this integration technique isn't just about ticking a box on a math test. It's about equipping yourself with a tool that's genuinely useful for solving problems in other disciplines. Okay, so let's move on to slide 6. Now, we've spent the last few slides learning a new technique, integration by completing the square, and working through the algebraic steps to make those integrals solvable using formulas we already know. It's easy to get caught up in the how of the method and wonder why we're even bothering. Think of it this way, we're building a toolkit of mathematical techniques. Completing the square for integration is one of those tools, and this slide is showing you that it's a tool that professionals actually use. Now, in the next slide, we'll start working through some concrete examples to really solidify how this all comes together. We'll begin with a rational function and then move on to an irrational function, so you can see the method applied in both scenarios. Example 1, rational function. Okay, let's tackle this example. We're going to evaluate the integral of 1 over x squared plus 4x plus 13 with respect to x. Remember from the previous slides, our goal is to use completing the square to transform the denominator into a standard form that we can easily integrate. So let's focus on the denominator, which is x squared plus 4x plus 13. The first thing we do is identify the coefficient of the x term, which is 4. Next, we take half of that coefficient, so 4 divided by 2 is 2. Then we square that result. 2 squared is 4. Now, this is the crucial part of completing the square. We rewrite the expression, adding and subtracting this value, 4, within the denominator. This gives us x squared plus 4x plus 4 minus 4 plus 13. Notice we haven't changed the overall value of the expression, we've just rearranged it. Now the first 3 terms, x squared plus 4x plus 4, form a perfect square trinomial. This factors nicely into x plus 2, all squared. And simplifying the constants, we have negative 4 plus 13, which equals 9. So our denominator now becomes x plus 2 squared plus 9. This allows us to rewrite the original integral as the integral of 1 over x plus 2 squared plus 3 squared. With respect to x, see how much cleaner that looks. We've transformed it into a form that's much closer to one of our standard integral formulas. Now, let's simplify things further with a u substitution. We'll let u equal x plus 2. This means that the derivative of u with respect to x, which is do slash dx, is equal to 1, and therefore do is equal to dx. Substituting these into our integral, we get the integral of 1 over u squared plus 3 squared. With respect to u, notice how the integral is now entirely in terms of u. Now we can apply one of our standard integration formulas. Remember from earlier, the integral of 1 over x squared plus a squared dx is equal to 1 over times the arctangent of x over a, plus the constant of integration, c in our case, is equal to 3. So, applying this formula, we get 1 over 3 times the arctangent of u over 3, plus c. Finally, we need to substitute back our original expression for u, which was x plus 2. This gives us 1 over 3 times the arctangent of x plus 2 over 3 plus c, and that's our final answer. So, to recap, we completed the square, made a u substitution, applied a standard integral formula, and then substituted back to get our answer. This process allows us to integrate even complex rational functions. Remember this method, as it will be very useful in future problems, especially when we encounter more complicated integrals. Example 2, irrational function. Okay, let's tackle another example, this time with an irrational function. We're going to evaluate the integral of 1 over the square root of x squared minus 6x plus 5 with respect to x. Step 1, complete the square for the expression under the radical. Now, remember from our earlier slides, the key to these problems is always completing the square. We're focusing on the expression inside the square root, x squared minus 6x plus 5. To complete the square, we look at the coefficient of the x term, which is negative 6. We take half of that, which gives us negative 3. Then, we square negative 3, which equals 9. So we rewrite the expression as x squared minus 6x plus 9, and then subtract 9 to balance things out, and add the original constant 5. This gives us x squared minus 6x plus 9, minus 9 plus 5. Simplifying this, we get x minus 3, all squared, minus 4. This is now in the form we want, a perfect square minus a constant. Step 2, rewrite the integral. Now we can rewrite our original integral using this completed square form. The integral becomes the integral of 1 over the square root of the quantity x minus 3 squared, minus 4, with respect to x. Step 3, use substitution. Next, we'll use a simple substitution to simplify the integral further. Let's set u equal to x minus 3. This means that the differential due is equal to dx. Substituting these into the integral, we get the integral of 1 over the square of u minus 2 squared. With respect to u, notice how this now looks much more like the standard integrals we discussed earlier. Step 4, apply the standard formula. Now we can apply one of our standard integration formulas. Recall that the integral of 1 over the square root of x squared minus a squared dx is equal to the natural logarithm of the absolute value of x plus the square root of x squared minus a squared, plus the constant of integration c in our case, a is equal to 2. So, applying this formula, we get the natural logarithm of the absolute value of u plus the square root of u squared minus 2 squared, plus c. Step 5, substitute back u equals x, $3. Finally, we need to substitute back to express our answer in terms of x. Remember that we defined u as x minus 3. So, substituting this back into our expression, we get the natural logarithm of the absolute value of x minus 3 plus the square root of x minus 3 squared minus 4, plus c. Simplifying the expression under the square root, we have the natural logarithm of the absolute value of x minus 3 plus the square root of x2 6x plus 5, plus c, and that's our final answer. Remember, completing the square is the crucial first step, and then it's just a matter of substitution and applying the correct standard integral formula. We'll be looking at common mistakes in the next slide, so pay attention to those to avoid them in your own work. Common mistakes to avoid. Okay, let's move on to slide 9. This slide is really important because it highlights some of the most frequent errors students make when tackling these integration by completing the square problems. Paying attention to these will save you a lot of frustration. First point, sign errors during completion. When we're completing the square, we add a term to make the quadratic expression a perfect square, but then we immediately subtract that same term. It's crucial to remember that addition and subtraction are opposites. If you forget to subtract the term you added, you're changing the entire value of the expression, and your integration will be off. So, always double-check that you've maintained equivalence by adding and subtracting. Next up, forgetting the coefficient. Now, this is a big one. Remember how, in the step-by-step process we discussed earlier, the very first thing we did was factor out the coefficient of the x squared term, that a value. If a isn't equal to 1, you absolutely must factor it out before you start trying to complete the square. If you skip this step, the entire process will be incorrect, and you won't get the right binomial when you rewrite the quadratic. Moving on to substitution errors. We've been using substitution, replacing parts of the integral with u, to simplify things. A common mistake is forgetting to actually replace dx with do in your integral. Remember, do represents the change in u with respect to x, and it's essential for correct integration. Also, don't forget to substitute the original expression for u back into your final answer after you've integrated. It's easy to get caught up in the integration and forget this final step. Finally, incorrect formula selection. This is where knowing your standard integral formulas really pays off. When you've completed the square and have an integral involving a square root, you need to carefully look at the expression under the square root. Specifically, pay attention to the order of terms. Is it in the form of a squared minus x squared or x squared minus a squared? The order matters. If you mix those up, you'll end up using the wrong inverse trigonometric function, either arcsine, sin inverse, or natural logarithm. So keep these common mistakes in mind as you practice. We'll now move on to the final slide, which summarizes the key takeaways from this entire section. Key takeaways. Okay, let's recap everything we've learned about integration by completing the square. This is our final slide, and it's designed to solidify the key takeaways. First, let's talk about the purpose of completing the square. Essentially, we use this technique to take a general quadratic expression, that's a quadratic in the form of a x squared plus bx plus c, and rewrite it into a more manageable standard form, which is x plus h squared plus or minus k squared. Remember, this transformation is crucial because it allows us to apply the standard integration formulas we discussed earlier. Next, the core step. This is something you really need to remember. The term we always add and subtract to complete the square is b over 2a all squared. So, if you ever get stuck, that's the key value to calculate. It's derived from taking half of the coefficient of our x term, that's b over a, and then squaring it. Now let's look at the integration path. This outlines the steps we take when tackling these integrals. It's a four-step process. First, we complete the square as we've practiced. Then, we perform a linear substitution, usually letting u equal x plus b over 2a, which means do will be equal to dx. After that, we identify which of the standard integration formulas applies to our transformed integral. And finally, we back substitute to express our answer in terms of x. Finally, let's look at the standard forms and what types of integrals they lead to. If you have x plus h squared plus k squared, this generally leads to either an inverse tangent, that's tan to the power of -1, or a natural logarithm, depending on whether that entire expression is under a square root or not. Similarly, if you have x plus h squared minus k squared, you'll also end up with either a natural logarithm or an inverse tangent, again depending on the square root. And lastly, if you have k squared minus x plus h squared, this will lead to either a natural logarithm or an inverse sign, that's sin to the power of -1, once again, depending on whether it's under a square root. So, to reiterate, mastering completing the square unlocks the ability to integrate a much wider range of functions. Remember these steps, practice the examples, and you'll be well equipped to handle these types of integration problems.